All right, so the first thing we got to review is that there are essentially two types of binary compounds. Okay, those two types of binary compounds are ionic and molecular. Okay, now, what does an ionic compound have in it? Anybody remember? Okay. A metal and a non-metal. How do I know where the metals are? How do I know which things are metal? Right, I look on the periodic table. Okay, periodic table is divided not in half, obviously, but okay, it's divided into two sections by the staircase. Okay, you'll see that slightly emboldened on your periodic table as well. Anything to the left of the staircase is a metal. All right, now there's varying degrees of metals. Okay, the stuff that's kind of near the staircase is often referred to as metalloids. Okay, they're a little strange. Okay, there's transition metals. They're kind of ones in the middle. They have kind of strange behaviors, but the more towards the left you get, the more metallic things become. Okay, so hydrogen, even though it's a gas, is the most metallic substance there is. Okay, metals typically want to give away electrons. Okay, that's what makes them metallic. Okay? Being metallic means you want to give away electrons. So hydrogen wants to give away electrons like crazy, right? The reason it wants to do that is it wants to essentially have a full or absent outer shell of electrons, which we'll talk about later. Okay, hydrogen only has one electron. By giving it away, it's all happy because it doesn't have to worry about it losing it or whatever. Okay, it's just gone and it doesn't have to take care of it anymore. Right. So anything that wants to give up electrons is going to be metallic, okay, or metal. Non-metals obviously are on the other side, okay, and so we're going to have, you know, things that would be gases or soft, not generally what we would determine to be metallic. All right, molecular compounds are made up of two nonmetals. Okay, so an ionic compound is a metal and a nonmetal. Molecular compounds have two nonmetals. The structure of these compounds is very, very different based on what happens to the electrons between the two atoms. Okay, and that's what we'll talk about here coming up. All right, the other thing we got to be able to do is write the proper formula and proper names for all of these chemical compounds. That's the part that will be mostly review, but there's a couple of things that I'm going to add that you haven't done before. Okay. So ionic compounds occur when a metal from the left side of the periodic table and a nonmetal from the right-hand side of the periodic table react to form a new molecule. Okay, so a molecule is two or more atoms joined together chemically. Okay, that includes compounds, or sorry, not compounds, but that includes molecular elements. Oxygen, for example, is a molecular element because it actually comes as a molecule, not as single atoms. Okay, everybody with me there? So anytime you have two or more atoms joined together, you have a molecule. Okay, so in these molecules, electrons are typically lost by the metal and they're gained by the nonmetal. Okay, thus both elements will have an outer shell of electrons that are full, and that is they'll be most like their nearest noble gas. The noble gases are the ones on the far right-hand side. So helium, neon, argon, krypton, xenon, and radon, okay, are our noble gases. They are basically completely unreactive. They never get involved in chemical reactions. They're never in compounds with anything else because they have an outer shell of electrons that is full. They're happy. Okay? The meaning of life for like all elements is to get an outer shell full of electrons, okay? No matter how they do it. So if we're looking at an easy example here, we'll look at sodium and chlorine because when they go together, they make sodium chloride, which is commonly called salt, okay? Which is bad because the term salt actually means any ionic compound. Okay, salt is a general term referring to any ionic compound because all ionic compounds are crystalline solids at room temperature. They are salts. Okay, so sodium chloride is in particular table salt. All right. So if we have sodium, okay, so a sodium atom, if we look it up on the periodic table, has 11 protons. Okay, now this is where Bohr's model still comes into play. Okay, Bohr's model did talk about the arrangement of electrons, and it's still somewhat correct, right? So for a sodium atom, it will also have 11 electrons. In the first electron shell, okay, there are 2 electrons. Only 2 can fit there because it's small. Okay? The next shell outwards can hold 8. Okay, and they tend to pair up like that. There's a repulsion between the pairs, okay, but they get forced together into these little groups. How many electrons is that now? That's 10. All right. This last shell only has 1 electron in it, but it can hold 8. So for sodium to have a full outer shell of electrons, it's either got to pick up 7 more or dump 1. Which is easier? Dump 1. Yeah, it's way easier to dump 1 electron than it is to find 7 more. That's why it gets along so well with chlorine. Okay, chlorine has 17 electrons. Okay, so it's got 2 in the first shell. Okay, it's got 8 more in the next shell. Sorry, that's not a very good drawing. Okay, and it's got 7 in a shell that can hold 8. Easier to find a home for 7 or pick up 1? Pick up 1. That's why they get along so well. Okay, so these two things react and they form an ionic compound. Okay, sodium will give its electron to chlorine. Now they both have a full outer shell of electrons. However, they are now also both charged particles called ions. Okay, what charge does sodium now have? Positive 1, because it now has 1 more proton than it has electrons. Similarly, chlorine now has a charge of negative 1 because it's picked up an extra electron and now has 1 more electron than it has protons. Okay, so this is what happens in an ionic compound. Okay, they trade electrons and they form this molecule. The bond is not very strong. Okay, the reason it's not very strong is both atoms got what they wanted. And this is going to sound terrible, but don't put it in a sociological context, okay? They both got what they wanted. There's absolutely no reason for them to stay together now. They both got what they wanted, okay? I know, again, that sounds terrible, but that's how, unfortunately, ionic bonds work. They're not very strong, okay? Because there's nothing now to hold them together, okay? There's nothing there now to hold them together. So what happens typically when you take an ionic compound and put it in water is an ionic compound will very quickly dissolve. Okay, it'll dissolve, and now what you have floating around in that solution is charged particles. You have positively charged sodium ions, you have negatively charged chlorine ions. They're no longer bonded together, they're just floating around in the solution. Okay, so they will dissociate very quickly. It's not a strong bond. Okay, everybody all right with that? So what you really need to get out of this is that in ionic compounds, electrons are traded, okay, and the bond is weak. Right? That's what you need to know about ionic compounds. Okay, and that's why we have this little meme here. The name's bond, ionic bond, taken, not shared. Okay, yeah. I know it's only funny if you're a science guy, but it's still funny. All right, questions on the nature of ionic compounds? Okay, so like I say, really all you need to know is electrons are traded, okay? Bond is weak, metal and a non-metal. All right, when it comes to naming ionic compounds, okay, there's some rules to follow. The rules for ionic compounds are more complex than they are for molecular. Molecular is actually quite easy, okay? But for ionic compounds, there's a number of different rules we have to remember, okay? The first thing is that we name the metal first and the non-metal second. We just start from the left and go to the right. Okay, that's how an ionic compound will work. Start on the left with the metal, go to the right with the non-metal. Okay, the non-metal's ending is always going to be changed to ide. Okay, so we don't say sodium chlorine, we say sodium chloride. Okay, that tells us that these two things are bonded together. All right, so we would have things like magnesium oxide, sodium fluoride, aluminum sulfide. Okay, those would be simple binary ionic compounds. Okay, everybody all right with that? All right. If I was looking at, let's say, this particular compound, what would I call that? Calcium chloride. Does it matter that there are 2 chlorines? Nope, not for naming purposes, it doesn't. Okay, for ionic compounds, we never use prefixes. There's always a temptation to do that. Okay, but in ionic compounds, we don't have to because there's only one way that chlorine and calcium can go together. and that's because of the nature of their charges. Calcium has a charge of +2, which means it needs 2 chlorines in order to make it happy, because it's got 2 electrons it needs to get rid of. Okay, and chlorine can only pick up 1, so it needs 2 chlorines. So these things only ever go together in that way. That's why we don't have to use a prefix. If we say calcium chloride, we know that's going to be CaCl2 because it's the only way they can go together. Okay, you might recall this from grade 9, the drop and swap, or swap and drop, whichever way they said it. Okay, you take the 2, you drop it over here, take the 1, you drop it over here, and you've got your formula. Okay, is that ringing a bell? The drop and swap? Okay, if it isn't, don't worry, it's really easy. We just swap the numbers. Okay. All right. So we name the metal first, non-metal second. We don't use any prefixes. All right, so we got to remember to name both ions. And the other thing, and this is the hardest thing for people, these are not proper names. So they're not capitalized unless you're starting a sentence with it. Sodium chloride is my favorite thing to put on fries. Okay, then you would have to capitalize the sodium. But otherwise, it is not a proper name and thus should not be capitalized. Okay, so when you're using the formulas, okay, the other thing to remember is that the charges of this compound have to balance. That is, an ionic compound has a net charge of 0. There are as many positives as there are negatives. Okay, and that's why we do the drop and swap. Okay, if we're looking at aluminum and chlorine, okay, aluminum has a charge of 3+, chlorine has a charge of -1, so I would need how many chlorines in order to make this work? 3. Okay, that's why when we drop and swap, this always works out. 1 aluminum, 3 chlorines, and I've got, okay, a net charge here. Now I've got 3 positives and 3 negatives. The net charge is 0. Okay, so the swap and drop always make sure that that's true. All right. Questions on that part? Is okay with that? Okay, because we're going to have time to practice this. Don't worry, this isn't the thing I'm going to teach you one time and then test you on right away. Okay, we're going to have some time to practice the naming stuff. All right, I want you guys, actually, we'll walk through a couple of these first, okay, and then we'll have you guys try a few. All right, obviously we've done this one already. If I was naming this one, it would be sodium chloride. Okay, I name the metal first, sodium. Okay, and then I write the non-metal with an "ide" ending. Okay, K stands for potassium, so I would write potassium because it's the metal. Okay, metal always comes first. Okay, and then I would name the non-metal. F stands for fluorine, so this stuff would be potassium fluoride. Okay, everyone kind of following my pattern here? Okay, for number 3 here, I've got hydrogen, and hydrogen is listed first, so it's behaving as a metal or non-metal? Metal, okay? Now, this is the weird thing about hydrogen. It's the most metallic substance we have, but it actually behaves as a non-metal sometimes, okay? If it's listed first, it's acting as a metal. If it's listed second, like in this compound, it's behaving as a non-metal. Okay, that's a molecular compound called methane. It's fart gas. Okay, that's the smelly stuff. All right, so this stuff here would be hydrogen iodide. Okay, just change the ending to IDE. Okay, what's Ca stand for? Calcium. Okay, and Br is bromine, so this is going to be calcium bromide. All right, so you are going to need your periodic table out now because you'll have to look some of these up. And I want you guys to try 5 through 8. All right, I'll give you a couple minutes and then we'll walk through those and see how. Okay, let's have a look at these ones here. So for number 5, okay, we have aluminum with astatine. Okay, so this is going to be aluminum astatide. Okay, again, remember, no capital letters on these. Okay, question number 6, we've got cesium with sulfur. All right, again, doesn't matter the numbers here. This stuff is just going to be cesium sulfide. All right, for number 7, we have Na, which is sodium, with O, which is oxygen. So this is going to be sodium oxide. Again, the numbers don't matter here. Okay, and then for number 8, we've got barium with selenium. There's actually 2 ways you can write this. It could be barium, okay, selenide, or it could be barium selenamide. Okay, it all depends on how you write it. There's different ways to say it, just like there's different ways apparently to say aluminum. All right, because the International Union for Physics and Applied Chemistry actually changed the name of aluminum back to its original pronunciation. Okay, so even though on our periodic table it says aluminum, on the newer periodic tables it says aluminium. Okay, I don't know why. I hate the sound of aluminium. I do not drive an all aluminium truck. Just doesn't sound right. I don't drink pop out of an aluminium can. Just doesn't sound right. Okay, so I will say it is aluminum because I'm stuck in my ways. I'm too old to change. Okay. All right, I'm going to have you guys try the rest of these and see how you do. All right, so for number 9 here, we've got radium with tellurium. So this will be radium telluride. All right, for number 10, we have lithium and fluorine. So this will be lithium fluoride. For number 11, we have rubidium and sulfur. So this will be rubidium sulfide. Okay, for number 12, strontium with iodine. So strontium iodide. Okay, and for number 13, we have calcium and oxygen. So this will be calcium oxide. And then for 14, we've got magnesium with selenium. So this will be magnesium selenide or selenamide. Either way is fine. Okay. Questions on any of those? All right. Now, there's a couple of metals that behave differently. Okay, so if you're looking at your periodic table, you'll see that some of the metals in the middle, like manganese, iron, cobalt, nickel, copper, okay, ones like that, okay, they have more than one charge listed beside them, okay, where pretty much everything else has just one charge. Like chlorine is always -1, sodium is always +1, okay, but these metals in the middle have more than one possible charge, okay. What that means is, depending on the situation, some of these metals will lose different numbers of electrons when they combine to form a compound. So, for example, with iron, okay, iron sometimes loses 2 and sometimes loses 3. Now, they are listed in order of their occurrence, right? So, the most common charge for iron, according to your periodic table, is the one listed first, which is 3. Okay, so more often than not, iron loses 3, okay, as opposed to 2. All right, everybody with me on that? Okay, so we're sorry, is it 2 or 3 on yours? I have 2 on mine. Is 2 listed first? From left to right? 3 is listed first on yours. Okay. Weird. All right, so the most common charge then for iron is going to be +3. Okay, and that's if you're not told otherwise, that's the one you would go with. But you're going to get told otherwise most of the time because it matters. Okay, so here's the situation we're dealing with. Any metal that has more than one charge is referred to as a multivalent metal. Okay, that is, it has different numbers of electrons in its outer shell. So the problem we can run into is this. If iron reacts with oxygen, it can form this compound, or it can form this compound. Okay, if the iron has a 2+ charge, it'll form this compound. If the iron has a 3+ charge, then when we drop and swap, we get Fe2O3. Here's the problem we run into. Those both have the same name. They're both iron oxide. Can that be a problem? Yeah, it's the same problem I have. Okay, I have, or actually, well, I have it again this year, but I've had it in the past where I had two kids with the same first and last name in the same class. Okay, weird, but it happens. Okay, and it's a problem because when I call out their name, two people answer because it's legitimately both their names. All right, I can't have this situation happening because let's just say that FeO is poisonous and this is rust. Okay, I mean it's not, but let's just say that for now. Okay, that's the case. So I'm writing this big long paper about the effects of salt on metals, and you get this iron oxide. But if you eat the iron oxide, it helps with your hemoglobin. I'm making all this up. It's not true. Don't do that. Okay, it helps your hemoglobin. Somebody reads my paper and goes, "Oh, well, I'm just going to eat iron oxide," but they eat this stuff. I mean, they're going to die either way. You shouldn't eat rusted metal. But let's just say that one is like acutely poisonous, okay? And they eat it and they die. That's kind of my fault. Kind of. Okay? Because they both have the same name and I didn't clarify which one is which. So there has to be a way to tell people which iron you are dealing with so there isn't any confusion. So what we do is we write out the name using the normal ionic naming rules, iron oxide, but then we put a Roman numeral beside the metal to tell them which charge it had. That way they know that when they want to write this, they're going to go, okay, this was the iron that was 2+, oxygen's always 2-, so when I drop and swap, I get this. Whereas if I wrote it like this, iron Roman numeral 3 oxide, I would know to do this, Fe 3+, 2-, and when I drop and swap, I'm going to get 2 and 3. Okay, and then people won't get confused and they won't eat something that's poisonous thinking they're eating something that's not poisonous because I've had some way to show that these two things are different. All right, so we can write their names differently based on their charge. All right, so let's try one here. Let's look at what would I call that stuff? Okay, so I'm going to write, first off, it's going to be copper sulfide, right? I'm going to write out according to the normal ionic naming rules that this would be copper sulfide, okay? But now I have to figure out which charge did copper have in this compound, okay? So what I have to do is I can't look at copper because it could be 1 or 2, but sulfur's always got a charge of -2, okay? So I've got 2 negative charges here, and I know that my compound always has to equal 0. All right, that means I need 2 positive charges from these 2 copper atoms. That means each copper atom must have a charge of 1. Okay, all right, so that gives me copper 1 sulfide. Right? So I just got to do a little tiny bit of math. Okay, nothing real hard. Okay, I just look at what the charge on the non-metal is and figure out what the charge on the metal is from there. All right. Now, probably a few of you noticed that, well, Coderre, that seemed like a lot of work. You did a bunch of math when all you had to do was reverse the drop and swap. Yes, in that case, but that doesn't always work because sometimes we reduce the numbers. Okay, if I had, let's say, I need one. Let's say I had this. Okay, I have CuO. According to that, they're both what? Well, yeah, they are +2, but if I reverse the drop and swap, I've got 1 and 1. Is that going to be right? No. Okay. Reversing the drop and swap will work about 2/3 of the time. On a quiz, which third do you suppose I'll choose? Right? I'm probably not going to choose the third where reversing the drop and swap would work. Okay, so what we want to do is go, all right, oxygen's always a -2. Okay, there's 1 oxygen. This has to add up to 0. There's only 1 copper, so its charge must have been +2. This stuff is copper 2 oxide. Okay, it's not hard math, it's just a little bit of making sure it equals up. Okay. All right, so that should be new. You probably didn't learn that in grade 9 science. Okay, usually they don't go over multivalent metals in grade 9 science. All right, so I want you guys to try the first 4 here. I'll give you a few minutes on those, and then we'll walk through them here. All right, so first thing I do is I write out the name of the metal, iron. Whoop. Okay, and the name of the nonmetal. Okay, so this is iron oxide. Okay, then I want to figure out what charge this iron had. The charge on oxygen, which I can find on my periodic table, is always -2. Okay, so how many negative charges are there in this compound? 6, because there's 3 oxygens right here, right? It's O3. So there's 6 negative charges here. That means I need to get 6 positive charges out of this. I only have 2 irons to get 6 positives out of, so each iron must be 3. Yeah? So we got iron 3 oxide.